Lab 4 Oscillation. Intro. The purpose of this lab is to analyze and model the motion of a spring mass system that oscillates in an arc using fundamental physics principles and computational techniques to understand and predict its behavior. This lab consists of two parts. Part 1 of this lab consists of analyzing a video of a mass hanging from a spring that is released and oscillates. The tracker is used to analyze the 2D motion of this mass and to graph its position. Part 2 of this lab consists of recreating the computational model of the experiment from the video and glow script. Models and fundamental physics principles used. I use Newton's second law because it allows us to find the net force acting on our system. We also derived F net equals the force of the spring plus force of gravity, and the position update formula and velocity update formula. I also use the energy principle because it allows us to find the changes in the system by only focusing on changes in energy. This consisted of the kinetic energy formula, the spring potential energy formula, and the gravitational potential energy formula. A brief preview of our results is that the computational model and experimental model were very similar with slight deviations as time went on, and that the change in energy stayed at 0 throughout the entire experiment. Our systems and surroundings. Systems was the spring, object, and earth, and in this experiment we had no surroundings. Our experiment was isolated. Our initial conditions in tracker were that the mass of the object was 0.402 kilograms, the length of the spring was 0.7 meters, and the initial position of the object was shown here, and the velocity was 0. Finding unknown initial conditions. So for the experiment, we also had to find the period of oscillation, which we found by taking the average for 3 peaks on our tracker, and we found that to be t equals 1.519 seconds. Then with t, we were able to plug it into this formula and solve it for k, which is the spring constant, which we found to be 6.878 newtons per meter. We also had to know the initial length of the spring before it was stretched. To find that, we set the magnitude of the force of gravity equal to the magnitude of the force of the spring because there's no other forces acting on our system. We replace those with their individual formulas, and we're able to get a formula to solve for the initial length, and we find it to be 0.1272 meters. Here's part 2, our glow script code. First, we set the initial conditions, the ball mass, position, velocity that we found earlier, some constants, and then the unknown initial conditions that we found. We can also solve for the length of the spring, the direction of the force acting on the force of the spring, and the stretch of the spring. And then we calculate the kinetic energy of the object and the gravitational potential energy of the object and the spring potential energy as well using these formulas right here. And we calculate the total energy as well by adding all those together. Continuing on, we find the force of gravity acting on the object, force of the spring acting on the object, net force acting on the object by adding those two together. And then we can use that net force to find the velocity using the velocity update and also the position using that velocity we just calculated using the velocity update. We update the values that we just calculated on the last slide, the length of the spring, direction, the stretch, and then we calculate the change in energy by subtracting the new energy from the previous one that we got from the previous slide. So this glow script code doesn't actually simulate our experiment. We have to put the x and y values of our object into the experiment. So we take it from tracker, make it into an Excel CSV, and then we input it into our glow script, and this is what we get. Results plus, what does it mean? So we have to answer the question for your model, is the energy principle satisfied? The answer is yes. Earlier we said that the system was both the mass, earth, and the spring with no outside forces. This means that the experiment should never lose energy as it's always conserved in the system and was never lost to surroundings because there are none. Our results showed that as one type of energy may be lost or gained, another is oppositely gained or lost to compensate for it, resulting in the change of energy delta E in orange on our graph, result for the entirety of the experiment to be 0. So you can see our graph, delta E, the middle line, is always in the center at 0. What does it mean? Part 2. Using the data you obtain in tracker, make 2 separate estimates of oscillation periods, first by estimating with x and second with y. So using the same method from earlier, we estimated that the period of oscillation for y on average was 1.519, while the one for x was 1.646. The difference could be caused by unknown forces, gravity acting on the y, or mistakes in tracking. This difference can also have major effects on our calculations of values like spring energy, spring constant K, etc. Some possible sources of error from my experiment were that human error during part 1 with tracking the object and inputting the middle of the object, the outside forces acting on the object during the experiment, and possibly faulty code and calculations.